meet before all of this madness began. We had a very good time, and now I'm happy that we can meet again, at least virtually. And so my thank you to them. All right, so let me start my talk. It's a bit different. This topic is maybe this series of webinars. I hope you will find it interesting. I try to make it as accessible as possible. We're going to talk about PDE, some PDEs, and some harmonic analysis. So precisely what we will be talking about, the initial value problem. Let me write. We study the initial value problem for the wave equation. So by this I mean, this is the problem of given functions defined on the Euclidean space RD and real valued, find another function defined on the space with one more dimension. This, of course, this additional dimension will be interpreted as time. So find a function defined in the space with one more dimension, and such that this differential condition is satisfied at all points in space and time, and the given functions are attained as initial data for the function and for the derivative. Let me put a box here. Okay. So, of course, this is the PDE viewpoint. An important thing, during all this talk, we will have two viewpoints. One is the PDE one. This is PDE. This is a PDE viewpoint. The other viewpoint is the harmonic analysis one, the operator one, which I'm going to introduce in a second. Then it's obtained. If you treat the Laplacian formally as a negative number, just pretend this is a negative number. So these now turn, of course, if this is a number, there is no dependence on x. This is just a function of t only. This then is an ordinary differential equation, and if you solve it, it's a familiar ordinary differential equation, and if you solve it, you get these formulas. See, I am treating the Laplacian as if it were a number. So doing this, the solution to the PDE is just given by this formula. And of course, if you write, I don't know what happened, if you write sine and cosine as exponentials, you see that this is just the real part of this thing here. And let me highlight it. Okay, of course, here f is a complex valued function that carries the given functions f1 and f0 in the real and in the imaginary part. That's boxes. Okay, so in this talk, we will study this operator. Okay. Okay, now, so this was just to set the stage. Now let's go to the next slide. So of course I said treat the Laplacian as if it were a negative number, and now let's give some formal definitions. This is very easy, very simple stuff, but it's important to set the stage clearly. So let's define the Fourier transform. The Fourier transform is for a function on Euclidean space. The Fourier transform is given as this integral. I will use both the calligraphic F and the hat notation for the Fourier transform. Both are very common. And I will use the PD normalization for the Fourier transform. Fourier transform is important for us for the very well-known fact that the Laplacian, which by definition is the sum of the pure derivatives of all pure second derivatives, the Laplacian can be obtained by multiplication by a suitable function. And this motivates the definition, which I'm going to give next. Oh, sorry. Okay, so definition for every function measure. Of course, here I am sweeping under the rug lots of technicalities. This integral may not be well defined, but we can. Everything is to be. Think every function is smooth, and when it's not smooth, there is some density argument behind it. So for a function, also this function must be measurable, and so on and so forth. So let me resume. For any function defined on the spectrum of minus Laplacian, we can define an associated Fourier multiplier, which is given by mimicking the formula for the Laplacian above. We will also use the same construction on the sphere. And we will consider later functions of the Laplace-Beltrami operator. Okay, so having said this, now we have given a meaning. We have given a meaning to this operator, which appeared in the previous slide. Okay, so in the rest of the talk, we're going to study this operator, which is defined by means of this functional calculus. Now, I'm not going to use this viewpoint very much, but this operator is an important one of harmonic analysis because this is related to this is exactly the Fourier extension operator to the double cone. Okay, so in particular, this operator is the harmonic analysis version of the PDE operator we saw in the previous slide. And we will be using both viewpoints, the PDE one and the harmonic analysis one. This interplay will yield some interesting results. So to proceed to the results, let me give one more introductory slide. So one more introduction slide. And let me introduce the estimates known as Strickard's estimates by Robert Strickard, but these estimates also go by the name of Thomas Stein. This nomenclature is more common in PDEs, while this is more common in harmonic analysis. But in this case, both estimates are the same. Okay. So the Strickard's estimates tell us that for each dimension D, not one, at least two. The wave equation in dimension one trivializes, reduces to something which is degenerate. So let's forget about dimension one, at least two. So for each dimension, at least two, there is a constant. Such that we can bound we can control the norm of the LP norm of the operator we just saw by the L2 norm of an appropriate derivative. It's not a true derivative. This, of course, is defined in the sense of the previous slide by the functional calculus. And the power P is this one. Okay, so this is one of the main characters of this talk, and so let us highlight it. Okay, so in this talk we will talk about the best constant problem for this inequality. This constant C is not explicitly, it has been computed explicitly only in one case, and we're going to investigate the other cases. So before going into this, let me just write a remark. This inequality can look weird, but it's quite natural because the right-hand side is a kind of relativistic energy. And I'm not going to explain this. I am not the kind of guy who can explain this physical thing very well. But you can consult the book Analysis of Leavenworth. They explain it. The left-hand side is a measure of size. Okay, so this inequality is telling us that given an initial data, recall that in the PDE viewpoint, this was a complex valued function that carries the initial data to the wave equation. So given initial data, you can control the size of the wave that they generate by the energy of the wave at initial time. But there is a multiplicative constant which is unknown. The problem then is finding the the configuration that gives the best possible left-hand side, given that the right-hand side is normalized to a fixed value. So in other words, if I have a finite amount of energy, what is the best arrangement of this energy that gives me the biggest waves? Biggest in the sense of this. So formally, this is the problem of the best constant, and it has been solved by Foschi in 2004. Because he found that this function here, I'm going to write, of course, x is an element of RD here. In dimension 3, this function attains the maximum. Attain. Okay, so this function, one says that this function is a maximizer to this inequality. And we will see in this talk why this function indeed is a natural one. And indeed, with this theorem comes a conjecture in the paper of Damiano Foschi. Conjecture is that the same should be true for all dimensions bigger or equal to 2. The same means that this is a maximizer of this inequality in arbitrary dimension. Okay, and so now finally I can present my result. I have studied this problem a little bit, and during the years I started my PhD with this problem. And I have a couple of results which I would like to showcase here. So my results, the ones that I am presenting today, are the following. So the most important one is that the conjecture fails for even D, but it's very likely to be true, I believe it, for odd D, because of this result. It's in my paper from two years ago. So the conjectured maximizer of Foschi is a critical point of the ratio functional, or the functional that I am writing down, L2. Of course, here you have to put something, otherwise this is not, you have to put an exponent here, but otherwise this is not differentiable at 0. But which exponent you put, it's not really important. You could put 2 here, and it's the same. So, the conjectured maximizer of Foschi is a critical point of the ratio function. Of course, this is a necessary condition for this to be a maximizer of this ratio. And this necessary condition is satisfied only in odd dimension. So dimension 3, d equal 3, of course, is okay because it's odd. And indeed, in this case, Foschi proved that this is a maximizer. But even dimension is not. And I think this is quite surprising, and I'm going to explain why in one moment. So if dimension is odd, then F star is also a local maximizer. And this is in my paper with Felipe from just before the madness of the COVID pandemic. Okay, well, I said the result is surprising, and I think this is the case because for a very similar operator, we seem to have no distinction between even and odd dimension. This is kind of surprising. So the difference is that here I have no real part. Here I have the real part. Of course, this is the physical operator because this is related to the wave equation. And to the double cone. This is related to an unphysical equation. So no PDE. And is related to the one-sheeted cone. So it looks very similar, but its behavior is quite different. And to prove this result as being the Penrose transform. Which is a classical tool of PDEs. In PDEs, this is classical. This is somewhat old-fashioned, actually, as far as I understand PDEs, not much. But in the application to this kind of problems is new to the best of my knowledge. So let me explain a bit this Penrose transform. It's Penrose, of course, this is Sir Penrose. And this Penrose transform is something from the 60s. So it's something so classical that I'm not going to give precise references. But the point is, this is a compactification of space-time. Let's explore this. We want to map our space-time into a compact one. So compact means that we want to make time a finite interval and space a sphere. Okay, the advantage of this is that this is compact. So we can't do, we will see that it's a bit more tricky, it's a bit trickier than one may hope, because we will have to mix the space and time. So let me introduce the polar coordinates. So on Euclidean space, well, this is Minkowski actually, on Minkowski space, we have time is t, the space is x, and we write x as r omega, where r is just the distance from the origin, and omega is a point in the sphere, one dimensionless. All right. I don't know what I'm doing with this virtual keyboard. Okay. So, on the other space-time, the curved one, we have the time variable, we will call it capital T. The spatial variable, we will call it capital X, which is x0, x1, xd. This is, of course, a point on the sphere. So it's implicit that the sum of all of these is 1. And then I am going to introduce the polar coordinate as I'm writing. Okay, so this polar coordinate is the distance from the North Pole. Let's draw a quick picture. What are we doing here? This is, we are in a space of one more dimension. We have a sphere here. So this is our sphere. And of course, these are the Cartesian coordinates. Now, the generic point, capital X, we can also express it as a function of a point on the sphere one dimensionless, and this capital R, which is the cosine, and which is nothing than the distance from the North Pole. So this is why I call these coordinates the polar coordinates. Yes, the polar coordinates. Okay, this was important because now we're going to define our map. Okay, I don't know what I'm doing. All right, okay. So let's define the map. First, let's picture our flat space. We put R and we put T. And I'm going to introduce two more coordinates, as if it wasn't enough, which I'm going to call X minus and X plus. Okay, so these are just coordinate at 45 degrees. Now, let's do the same construction on the sphere. Let's put capital R and capital T. This is pi, this is minus pi. Capital R is, recall that capital R is the distance from the North Pole. So at most, it can be pi. And again, we put the 45 degrees coordinates here. And I'm going to call them X minus and X plus, and they are defined by the analogous relation. Of course, here I put 1/2, here I haven't. This is not essential, just for convenience. Now, having said this, we define a map of our flat space-time into our curved space-time by taking the arc tangent. And this is another important character, so let's highlight. Okay. This is the Penrose map. Now let's explore it a little bit as quick as possible. The best way to visualize a geometric map is always to see how it maps a grid. So let's take a grid in Euclidean space and let's see how it's mapped by the transform to the other space. So the vertical line here, the pure time, and I don't know what's going on, okay, the pure time is mapped to the analogous vertical line. Similarly, the horizontal line here is mapped to the purely horizontal line. These lines, horizontal, are mapped to lines which are attracted, to this point. And similarly on the lower side. And these vertical lines are mapped to lines which are attracted in the past by this point at minus pi, and in the future by this point at plus pi. So this is the picture. Of course, it's not great, but it's the best I can do. In particular, we see here, the image of this map is not the full Cartesian product. And this is going to be very important. So let's write it as a remark. P is not surjective. Its image is this triangular shaped region. This is the image of our map. And this is, it's given, it's easy to see that this is given by this inequality. And this is called the Penrose diagram. Of Minkowski spacetime. Okay, so people in this is of course is the simplest possible Penrose diagram. People in relativity use this kind of constructions to study infinity. If you shoot a ray of light here, it will travel along this direction, and here you will see that it will end up in this point. But if you stand still, you will travel along this direction, and no matter where you are, you will be attracted to this point at infinity. So for this reason, these points of the boundary are given a special name in relativity, and they use this to study asymptotics, long-time behavior of relativistic phenomena. We are not going to do anything of that, but it's important that we have mapped Euclidean space into a compact space. And the main property, now I'm going to state the main property of this map in a language suitable to harmonic analysis. Let's define a function. Let's call this function omega. And let's define omega at time 0. Let's call it, since it's important, let's give it a special name. Okay. Now, let me define for a function on Euclidean space, only space. This is time 0, initial time, the beginning of time. To a function in the beginning on space at time 0, associate a function given, denoted by the same, the same letter but uppercase on the sphere by this formula. And of course, I don't know what I'm doing. with this pen. Okay, so by this formula, take your function, multiply it by a suitable weight, and compose with the transformation we just defined. So don't pay too much attention to this. This is just a change of variable. This is the transform. So multiply your function by a weight and lift it to the sphere. This is what I call the Penrose transform. Okay, then we have two properties which are very, very useful. I think I find them very useful to the study of these kind of problems. And the first one is that, sorry, the solution to the wave equation, or the extension operator, the operator we saw before, up to, again, multiplication by a weight and recomposition with this change of variable, equals the solution to an analogous equation, but on the sphere. And not only that, but the transform is isometric. What does isometric mean? It means the thing that I'm writing down. Okay, so we have found a way of mapping solutions to the wave equations to solutions of another equation of the sphere, but note carefully that this is meaningful only, and sorry if I go back, but this is meaningful only in this triangular region. So a solution to the wave equation here is mapped to a solution to the wave equation in this space, but only this window is relevant for us. What happens here is irrelevant a priori. This is a very important feature of this transform. Okay, so now in the time left that is left, let's see how to use this transform to prove that critical point thing, that the conjecture maximizer of Damiano-Foschi is a critical point if and only if dimension is odd. So sketch of proof. So, okay, yes, I was going to say something about the Penrose transform, but I think I will skip it. Just let me say something. All of this I'm going to skip, but all of this is related to the theory of conformal mappings. We can discuss this, but the proof of these two properties is related to conformal map. I'm going to skip it because otherwise I won't finish my talk, but it's a standard fact of conformal theory, but I have rephrased it in the language of harmonic analysis. All right, okay. So let's erase this. So now we can finally prove. We now sketch the proof of the original result. Okay, so this is the critical point thing I was talking about a couple of minutes ago. So the first thing to notice is the maximizer that Foschi conjectured which equals F star, and I am following this notation. It's much easier up to Penrose transform because it's a constant. So this is why it was so natural. It's natural to conjecture that the best, when you are on the sphere, constants are available. So usually maximizers on the sphere, you teach me that maximizers are either constants or Dirac deltas. So Fosky conjectures that in this case they are constant. Now, having said this, let's see. We want to study critical points. So to study critical points, let me give a simple lemma. Lagrange multipliers. So only for this proposition, let me call S the operator we are studying, just for the sake of clarity. So we want to prove that this function is a critical point of the ratio. This is L2 and this is LP. Okay, well, I claim that this is the same as to say that there is a real number mu such that the derivative, the opposite, for all f in a suitable space. Okay, here, this scalar product I have introduced is the one that's adapted to this norm. Nothing deep here. Okay, so this is just a very basic thing. If you want to find critical points of this ratio, you can also rephrase it as a constrained critical point. And you have to check these conditions. So it's a corollary we have. This function is a critical point if and only if. Now I compute this derivative, it's quite easy, and this is the condition that we have to check. This integral is 0 every time this orthogonality condition is satisfied, because this is what we say. If this is 0, then this derivative must be 0, but this derivative is this integral. It's an if and only if, actually. It's quite easy to check. So this is the integral I'm going to study now. And okay, and now notice that important remark, the Penrose transform of this is 1. So this function here, this operator here, which let's recall was the real part of this. This is essentially up to Penrose transform. Recall we had a weight, but essentially this turns into this operator here but applied to the constant function 1. And now, the Laplace Beltrami of 1 is 0. So this is easy to compute. This is just forget about the Laplacian. Right? So forgetting about the denominator, this is a cosine. This is important. Okay. Here we see already that it is the importance of the Penrose transform. And so, applying the Penrose transform by Penrose, we are led to the integral okay. Of course, this wanted to be a sigma, but there's no more space. This sigma is the measure on the sphere, on the three-dimensional sphere. So notice that it's much simpler now. We would like to use Fubini here, but we can't because this is not a Cartesian product. In general, there's no Fubini. And now, okay, I'm running a bit low on time, but let me explain why. In odd dimension, there is Fubini. In even dimension, there is no Fubini. So let's see why. Quickly, as quick as possible. So let me quickly recall spherical harmonics. I'm going to use now spherical harmonics. As you see now, we leave PDEs and we go back into harmonic analysis. Let's recall spherical harmonic. So spherical harmonics are, let me denote by YLM an orthonormal basis of L2 on the sphere with this property here. Okay, so the familiar spherical harmonic. Also let for, okay, so for a function on the sphere, let f hat and n be the integral of the function against the spherical harmonic, the spherical Fourier transform, if you like. Now, this is the important thing. We have the operator that we are studying here. If you develop it in spherical harmonics, up to this real part, you will find, and I'm sorry that I have to go fast on this, but this is really one of the key steps. You will find that this is exactly, this is a square. When you develop it in spherical harmonics, here you get a perfect square. And so here you find something which is integer when D is odd, and half integer. This is the difference. This is the difference. Let me just explain this and then I finish. So here comes the difference between even and odd. And the reason of this is the following. So recall. Okay, so let me just say, so thus we have different symmetries for odd D than we have for even D. And precisely, so let's call this function capital U. So this capital U is 2 pi periodic and it enjoys an inversional symmetry This is for odd D. Whereas for even D, the only symmetry we have is this 4 pi symmetry. And now notice that we have on you remember the range of the Penrose map was this kind of triangle. And here we had minus pi, here we had pi, and here we had pi. This is a 2 pi long time interval. So you can see that in odd dimension you have the right periodicity. In even dimension, this is not good. So already from this, you can tell that in even dimension, you're going to have more work to do because the Penrose transform will be less useful to you. And also, this symmetry here, which unfortunately I can't prove in detail, but it's very easy, turns into, this is the last thing I'm going to say. The integral of the function, recall the integral we were studying was here. Okay, so this integral, we had the cosine, and we had this operator here. We call it U. We call it capital U. Remember, sorry that I'm going a bit fast. Capital U was this function here. Okay. So because of these symmetries, this integral turns into the same one, but on the full Cartesian product. And this can be done only if dimension is odd. And because using this enables the use of forbidden. And once you can use forbidden, you can use the orthogonality you have at the beginning of this proof to prove that this actually vanishes. So this implies, by Fubini, that the integral is 0 if if the orthogonality condition is satisfied. The orthogonality was this, and it turns into this. Okay. Okay, but this can only be done in odd dimension. Okay, I will stop here. Thank you. Should I write thank you? Oh, thank you for your attention. Thank you.
Okay, so let's see if we have any questions for Giuseppe.
I had a question. So right, there's the right in dimension 3, and I think it was your second or third page, but right, you were saying that there was that function f that was being defined was found to be a solution to provide a maximum in dimension 3. Was that found to be a unique solution, or if not, have others been found?
Yeah, no, of course it's not unique. If when you have a solution, just for example, just rotate space, you have another, translate, you have another, and so on and so forth. So it's proven that there is a group of symmetries, which, by the way, is the natural one for the problem, whatever this means, such that if you are a maximizer, then you come from that one by the action of this group of symmetries. So you can obtain new maximizer by acting this group of symmetries, and it's proven that this is the only way you can get new maximizer.
Okay, so I guess I paraphrase it. Like if you mod out by symmetries and translations and everything, then is the solution unique, or are there still other ones?
If you mod out symmetry, if you mod out the right symmetries, of course the solution is unique.
Okay.
And, yes, the right symmetries are the natural symmetries to the wave equation, which
right.
Lorentz boosts and all of this.
Okay.
So is this because on the Penrose side it's just constant, so it must be unique because you pull back to Penrose?
This is a nice observation. No, the proof of uniqueness is different. Mm-hmm. The original paper does not use the Penrose transform at all. Mm. It's purely Minkowski space. Yeah. Mm. It's very interesting. This is a very good question, actually, because I tried to find a way of proving this uniqueness by means of these techniques, but I couldn't. But this would be a very, very interesting insight. Yeah.
How about these other F stars? I mean, you said the other F stars, capital F stars for odd Ds, you said they were not one. What are they?
Yeah, this is another very good question.
Do you have like an explicit, function for them?
You can, yes, but this is weird because for your question, it's easier to express maximizers in Euclidean, I keep saying Euclidean, but it's Minkowski space-time. Mm-hmm. Because there you have explicit expression. You have time translations, rotation, usual business, and Lorentzian boost. These things, when you lift these symmetries to the Penrose side, you get a mess. So it's explicit, of course it's explicit, but it's more difficult. Penrose is a kind of stereographic projection. It's in the, yeah, it's somewhat, it's, for symmetries, it's easier to be on the flat side, on the Minkowski side.
Right, so that's why it's I see. So it's conformal, and so it's what sort of like stereographic projection.
It's exactly like stereographic projection, yes. Yeah.
Let's see, any more questions?
So I have sort of a stupid question. So this peculiar difference between the even and odd dimension in the sphere, are there some other geometric problems involved in the sphere where it's also observed?
Oh, nice one. Nice one. I'm not off the top of my head.
Okay, it's interesting. Yeah, because there are some issues, there are some problems involved in spheres where, for example, there are different answers depending on whether or not the dimension, the ambient dimension is 1 mod 4 or not. So there are several things of that, and that basically stems from the phase shift in the Bessel functions. But yeah, I haven't seen this particular thing before, so it's quite interesting.
Yeah, I agree. I don't know how to answer, but it's a
Okay.
Yeah.
Okay. Okay. Thanks.
Oh, can I ask a question?
Yes, please.
Oh, so you said that the original work was done without the Penrose transform. So how did they guess this F star, the form of this F star?
In the original work, it comes from the fact. If you can you still see my screen?
Yeah.
Yeah. So this comes from this. Now, up to constants, normalization, and the like. If you take the Fourier transform of this, you get an exponential. And the operator was this. So up to Fourier, if you Fourier transform this, you get this. So,
well, sorry, I don't see the screen. Do you guys see the screen?
Giuseppe, I also don't see what you're writing.
okay, let's see if I can.
So we can still see your screen share, but nothing changes in it.
Nothing changes. Okay.
Yeah, we just at the last slide.
Let's see what's going on. Technology, of course.
If you restart the share, that'll probably fix that.
That's what I'm trying to do.
Oh.
It's a, I don't really know what I'm doing, sorry. Maybe I will stop and try and share again. Okay. Now you should see a couple
Yeah,
of
okay.
Yeah, so this is the reason why. This is, you have an exponential, and the fact that you have that you have this function here and here is somewhat the reason why. So this is it's a bit unclear because the real explanation would require me to put it into the framework of extension. So adjoint restriction theory. It's let me see, think.
Okay, thank you.
It's yes, it's a for if you know, I mean, if you know, it's natural to let me write this for adjoint restriction to the hypersurface given by this equation, it is natural to expect a maximizer in the form exponential of this thing. Here we have minus, maybe with the minus, yes. Maybe with the minus here, yes. So we have this. Okay, so this is the somewhat the reason. It's a bit cryptic because I haven't used this viewpoint, but this is the reason why. So it's a Fourier. It comes from the Fourier transform. This is why they guessed the right maximizer.
Thank you.
Okay. Any further questions? So, Giuseppe, you said you proved that you have local minimizer for these odd dimensions. So do you actually
Yes.
like do you actually go ahead and check second order conditions, or how do you do that?
Exactly.
Mm-hmm. I see.
It's I mean, it's only a technical difficulty, but it's the same. It's the same thing. You use the Penrose. You check that you can do Fubini, and then you have computations are a bit. It's a computational difficulty, but it's not a conceptual. Conceptually, it's the same.
Mm-hmm.
Of course, you will have spherical harmonics and some computations to do, but it's not different from what you've seen here.
Let's see. Any more questions, comments? So we're still on record. We will go off the record for the shy questions later. But for now, any more questions on the record? Yes, so I just thought for Dima's question, where you get problems that depend on dimension or answers that depend on the dimension of the sphere, well, you can come up with some silly examples like when the sphere is parallelizable, right? So when you can attach a smooth vector field at every point. So basically you have a bunch of vectors at every point, and as you go from point to point, it's smooth. So this exists only on S1, S3, and S7, because these are the division algebra. So basically this goes back to Matthew's talk. So somehow quaternions, and whenever you have a division algebra, these dimensions are special. So you can parallelize spheres only in the case you have S1, S3, and or S7, but not say S2. So this is why there is this Cowlick theorem. You cannot comb a sphere, a two-dimensional sphere. Right?
Yeah, the hairy ball.
Yeah.
So you can comb S3.
Yep, apparently, and S7.
Okay. And S7. It's very interesting, actually. Thank you.
Let's see. Any more questions? Shall we go off record? Okay.